Cosets are really important in abstract algebra. We're going to see after spring break, we'll highlight, you should have read about this already though, that they're important for proving Lagrange's theorem. If you haven't read Lagrange's theorem and its proof, do that. You'll see that cosets are used in proving Lagrange's theorem. That's fundamental. They're also important in chapter 9 in studying what are called factor groups. And factor groups are, once again, helpful in our quest to classify groups. Okay, so these are all tools to help us in our quest to classify groups. You want to know and understand, even intuitively, coset properties like these, for example. It takes some time. You have to spend some time thinking about trying to prove these properties, studying the book's proofs, thinking about examples, working with these cosets a lot to get used to them. What are the ideas, I guess, since we got 3 things to prove here, of the proofs for these properties here? First one is the easiest. I am assuming H is a subgroup of G here. The book does define this notation, AH or A. Even when H is not a subgroup of G, you can still define such a set. However, we don't call it a coset unless H is a subgroup of G, and it doesn't have the properties that we like unless H is a subgroup of G. So we almost always think about this in the context of H being a subgroup of G. Almost never is H not a subgroup of G. And that's what we're assuming here in these properties. What about the very first property? Why is A an element of AH? The left coset of H in G containing A. It says it contains A in its name, but we better prove it contains A. Well, since H is a subgroup of G, that means the identity is an H, which means A times the identity is in AH, but A times the identity equals A. Done. Okay, so that one's easy. The first one. What about the second one here? That gets harder. And it is an if and only if. The left coset of H in G containing A, I'm going to try to say that every time. The left coset of H in G containing A equals H itself if and only if A is an element of H. Maybe a picture is helpful. Sometimes these pictures are helpful, sometimes they're not. There's G. Here's H. H is a subgroup of G, more than just a subset. In this picture, we only see that it's a subset, but we're also saying it's a subgroup, so it's also got E in it. It's also closed under multiplication. It's also closed under taking inverses. Where is A? A could be in H, it could be outside of H. If A is in H, then the left coset of H in G containing A equals H itself. If A is not in H, if it's over here, then evidently thinking about the contrapositives of both of these, evidently AH does not equal H if and only if H is not an H. That would be a true statement too. The left coset would be something other than H. It actually would end up being something that's completely disjoint from H, though that's not part of the statement. If A is not an H, then AH, which does contain A, turns out to not even have anything in common with H. It's disjoint from it. That's, again, not part of the statement, but it's true. It's another part of the lemma. Anyway, coming back to trying to think about proving this, which direction is easier? I think the direction that's easier is that direction. Assume the equality of these sets and prove that A is an element of H. Assume AH equals H. Prove A is an element of H. Maybe the fact that A equals A times E is useful again. A equals A times E. And E is an element of H since H is a subgroup of G. And by definition of AH, that's got to be an element of AH. But I'm assuming AH equals H. Done. That does it, right? A equals A times E. By definition of the left coset of H and G containing A, since E is an H because H is a subgroup of G, that's an element of AH. But I'm assuming AH equals H. Therefore, this line of equal signs and one element of symbol implies A is an element of H. Done. That's the easier direction. The harder direction is the right to left direction. Assume A is an element of H. Prove AH equals H. Prove a set equality. These are two sets. So we got to show one is a subset. The left is the subset of the right, and the right is a subset of the left. I think showing the left one is a subset of the right is a little easier. Prove AH is a subset of H. Give me an arbitrary element in here. Why is it in there? What should I call the other arbitrary element? Anything you want, maybe B. Why is B in H? Well, if I assume B is in AH, the left coset of H and G containing A, by definition of that left coset, that means there exists an H in capital H such that B equals AH. Why does that imply B is an H? Think about what you're assuming. You're assuming A is an H, and the little h is an H as well, and H is a subgroup, capital H is a subgroup, closure. That does it. That's in capital H, since capital H is a subgroup of G by closure. Therefore, B is an H. Therefore, AH is a subset of H. The harder inclusion is to prove the other way around. H is a subset of AH. Give me an arbitrary element of H. I've got to show that is it also in the left coset of H and G containing A. What would we have to do to prove that? We'd have to prove, by definition of this set, that there's some other element of H such that B equals A times that other element, right? If B is going to be in there. Must show there exists some other element, little h of capital H, such that B equals A times little h. Okay, this is just the idea of the proof, so I'm not going to be polished here. Let's do some problem solving. That would be equivalent to H being A inverse B, right? Left, multiply both sides of this equation by A inverse and change the order. And since B is an H and A is an H, and since H is a subgroup of G, that's going to be an H, capital H, closure, closure under both multiplication and inverses. That'll be the element that we need. I mean, the polished proof would probably say something like this. A, B, and H implies A inverse B is an H, since H is a subgroup of G, which implies, what am I trying to do? Trying to show the B that I start with is A times something in H. The something is going to be this thing. A times this thing use the associative law for emphasis, is the B. That's an element of A times capital H. That would be a little bit more what the polished logical order would be. Up here, this was more problem solving. It's still kind of just the idea of the proof because I'm not being careful about writing sentences. You're experiencing our common experience here. You get it for like 2 seconds and then it's gone. Got to continue to rethink about it until it becomes more clear. Last property was trying to prove that AH equals BH if and only if A inverse B is an H. Let's try this direction. Assume AH equals BH. Show A inverse B is in H. This feels a little trickier, I think. This kind of emphasizes that the author's approach is a little bit superior in this context. The author approaches this by relying on some other properties I haven't mentioned. Let's go ahead and talk about the author's approach. So we're assuming AH equals BH. What the author does is says, well, effectively multiply both sides of this equation on the left by A inverse. Wait a minute, can we do that? Is that really a multiplication going on? Technically not, but effectively, yes. Technically not, but effectively, yes. In a sense, by writing this right here, remember by what we just proved a few minutes ago, if A is not an H, then AH, the left coset in H of H and G containing A, is not equal to H. It's not even a subgroup of H. So technically speaking, in writing A inverse on the left side of that, we're using this definition right here in the case where the H is not a subgroup. The AH playing the role of H is what I mean. And the A inverse playing the role of the A. We are really saying this is a new set consisting of all elements of the form A inverse times something in that left coset. But I am going to end up thinking of it as a multiplication because there's another property of cosets that I haven't mentioned yet that can be used here. This one's the one I'm thinking of right there. Kind of like an associative law. H is a subgroup of G in this lemma here. But for example, BH, if B is not an H, is not a subgroup of H. And this kind of expression right there that you see right there, ABH with the parentheses around the BH, is exactly the kind of expression we have right here. So I can use that property to say this equals A inverse AH, which equals EH, which does equal H since H is a subgroup. So E is an H. I can also use the associative law that I used right there here as well. I can write this as A inverse B H. Same associative law that I just showed you in the book is being used right there. And so what I've got here in all this is I got ultimately an equality between this and this. And that allows me to use the property we proved 5 minutes ago. This one. The left coset of H and G containing A equals H itself if and only if A is an element of H. the left coset of H and G containing A inverse B equals H if and only if A inverse B is an element of H. And this is actually enough to prove the other direction here as well, because these are all if and only ifs.